sorry. Are there any questions on anything before we begin today's tutorial?
Good morning. When are we going to receive our homework today? Or
Yes, today.
okay, and deadline will be at the 25th, right?
Yes, yes.
Yeah, okay.
Okay. Um, so what we need today is to look at how to use boosting trees, gradient boosting. I know that we will be focusing on other boost. Before I look at it in Python, just let me know if you have any questions or if you don't understand something from the lecture. I was a bit rushed, but hopefully either you understood or you looked at the links that I sent.
I guess
Okay.
the whole picture is understandable, but maybe some how to say uncertainty about the details. But I'm sure that today it will be more clear.
Okay.
And yes, sorry, before we begin, something is strange with your sound. Uh, it's like
mm,
you're using, I don't know, maybe another micro or just using speakers,
yeah,
another set or something.
yeah, let me check. How about now?
Say something again.
No, sorry. This was
No. Still remains the problem.
what's wrong?
Like your sound is interrupted sometimes and lagging, and when I'm talking I can hear myself as well.
I see. Um, yeah, no, I'm using the same setup. Okay, let me. How about now?
Still double in
Better?
sound.
Uh,
It's like we could hear your echo and ourselves while speaking.
does everyone have this problem?
Yes, there is a similar problem.
It changes now. Is it better? No?
No, it's not. It's the same, but it's okay for me.
Um, let me restart the Zoom. So please log in like in a second. I will start. Okay, how's it now?
Now it's perfect. It's just what it was before, I guess,
Okay,
for today.
yeah, I guess something is going on with my desktop. I'm connecting from a laptop. Okay. Um, yeah, let me share the screen. Yeah, I wanted to say something that I rushed through last time about the trees before we start talking about the codes. So, um, so we started with talking about not trees, the boosting algorithms. So trees by themselves are not so useful. Um, no, sorry, not that useful. They are not so good at forecasting or prediction tasks. Uh, but they have this nice feature that they're highly flexible. They allow to use unscaled data. They handle simultaneously. They can handle missing observations. They can handle um, missing observations for some explanatory variables. They can provide interpretation of the results. So that's why they're uh, highly popular, but as a prediction tool, they're not so good. Now, but we needed to go through them because they make the basis of uh, boosting. Now, boosting it's a general procedure that can be um, applied that can be implemented through any way of fitting some function to observe to outcome, function of features to the outcome. It can be trees, it can be whatever, but trees are the most popular way of implementing boosting. So the most popular algorithm here is gradient boosting trees. Now, uh, we talked about Ada Boost uh, to discuss as a first boosting algorithm. And the idea there was to combine many simple predictors uh, to each of which is potentially weak, uh, meaning that it doesn't predict any, like just gives a slightly better performance than semi-random chance. But by combining them, we get a strong predictor with predictions that are giving very quite low loss. Now, other boost is uh, is a very peculiar algorithm. And when it was introduced, the way it was introduced, how I introduced it on the slides, it was introduced in 1999 or 2001, I forgot. Um, it was introduced the way I showed it on the slides, and it seemed like a magic. Why would you do like exponential discounting and things like that? It was very strange, but it worked well. So it's kind of some very smart statisticians figured out how to construct an algorithm without realizing they were doing. Then 5 years later, people realized that ADA boost algorithm can be uh, represented as a stage-wise additive modeling algorithm with exponential loss function. What is stage-wise modeling is when you uh, try improve your forecasts in a sequential manner in each iteration, trying to predict parts of the data that you didn't predict well in the previous iteration. So this is stage-wise additive modeling. And I talked about its properties, that it's greedy and uh, um, what was the other one? Greedy and myopic. Myopic meaning that it optimizes only like one step at a time, and it doesn't improve the previous steps. Now, once you realize this, that ADA boost is just a particular example of a stage-wise modeling with exponential loss, you can start changing loss functions. The problem with changing loss functions is, and then we talked about why you might want to change the loss function from exponential to something else, or it's to be robust to outliers. The problem with changing the loss functions is that you don't get a nice efficient algorithms once you have some general loss function. And then that's where gradient boosting comes in. It works for any loss function, and it's a general procedure. And again, ADA boosting is a particular example of a stage-wise modeling, and gradient boosting is a more general approach that uses stage-wise modeling and general loss functions. And the big idea behind gradient boosting is that it tries to improve loss functions on each iteration in the directions of minimizing it, in the direction where it is minimized the most on each iteration. And the minimization is achieved by finding the derivatives of the loss functions in the data points, and then using some approximation of the derivative with some flexible function. And when we are talking gradient boosting trees, we are approximating derivatives with a tree. So that's the essence. When you are dealing with implementations of gradient boosting trees, so in general gradient boosting, all this stuff is kind of hidden from you. You don't really deal with this. So in that sense, it makes your life very simple. It's not different from lasso, ridge, or linear regression that we considered before. The only difference would be just choosing different hyperparameters. So let me start showing you examples. So let's play around here. Let me start sharing. Um, So this is the link to the notebook. 1 second. Uh-oh, I guess I didn't. I see, I didn't install. Strange. Oh no. 1 second. I'm trying to launch Jupyter. 1 second. 1 second. Hmm. Okay, let's there is an issue right now. need to address it. I'm reinstalling the whole thing on my notebook. Something is wrong. I think I didn't upgrade the Jupyter notebook to be able to connect to the local runtime. Let me talk about ARIMA and VR first, and then we will go back to trees. So let me open my notebook with VRs. Is it?
Isn't it in the end var? Like,
No. Yeah, okay. Okay, let me try this one. So we are going to do VR and ARIMA simultaneously because it's just I want to show how it works on a simulated data, and then we will apply it to the real data once everything is updated. It's my Jupyter is now taking forever to update. 1 second. Yeah, just give me a second. Apparently, it's not my day today. My desktop computer is going haywire. My laptop is not upgraded. Okay. Let's connect. Just keep one time. All right. But I could have used Jupyter Notebook instead of Google Colab. Okay, whatever. No, it's too late. Just 1 second. Yeah.
Perhaps you could show the screen on your computer and the sound from your laptop.
No, I can't. You mean show the screen? Well, no, now it's impossible. My computer, my desktop computer is now broken. There's something wrong with it's a very powerful but an old computer, and it's Mac Pro, like 2009 vintage, but it's very powerful. So I'm still using it, but there's something wrong when it's rebooting. It's takes like half an hour to get back to normal. Okay, so let's start. So I will start with simulating this time series jointly. Here, y doesn't depend on x, while x depends on y in the following sense that x has the value of x is 0.6 plus y. So y is a autoregressive process with a drift. The drift is 1. X is jointly y and x are VRs. So I'm going to simulate 500 observations of this series by drawing errors from a normal distribution. I will start with 1, the coefficients 0.8, 0 for x, 0.6, 0.5. So I give such matrices, and I um, simulate, I draw epsilons from a normal distribution. Yes, and sorry, and I make dependence between epsilon y and epsilon x, which is a general thing in VR processes. Right, sorry, I forgot. Let's key feature here in the example that I'm going to show is that uh, error of y depends on error of x through this matrix P, which is error of y is equal to has 0.5 correlation with error for x, while error for x doesn't have is not correlated with y. That creates this dependence, two-way dependence between y and x. So to generate this dependence, I draw V's from multivariate normal with 0, 1, with 0 mean variance 1. And then I make it a correlated matrix of errors by using this P inverse. What's going on?
We lost you for a few
Yeah,
moments.
even Zoom today gets crazy. I don't know what's going on. Today is not my day on so many aspects. As they say in English, when it pours, it rains. Such a bad day in so many aspects. Give me a second here. It's still updating. Okay. So I also, when I'm generating this time series, I generate the size of them 500, but I actually generate it's of the size 600, and then I drop 100 first observations. This is so-called heat up, and this is a usual thing to do when you're doing simulated time series. And so just to display how it looks. So y, x looks, I don't know, just sometimes serious, just eyeballing them, we cannot say much. Now, what I'm going to do, I'm going to first run a vector autoregression on these two series with different logs. So here, this is so-called vector autoregression. What makes it a vector is because there are two variables for each observation, there are two variables, y and x. The estimation of this is actually not so difficult. It's all implemented, and it's just a very straightforward generalization of ordinary least squares to the vectors. It's just a bit of algebra, but you can check it in any textbook. The beginning of VRs is very simple. You just have the data and you estimate it with uh, vector OLS, which is just a generalization of OLS to vectors. And when you're applying it in estimation in Python, you just call you create VR out of the process, and then you call fit. And here what I'm doing, I'm applying information criteria, Akaike, Bayesian. This is prediction error. And then this is Hanan-Kin information criteria. And what I'm doing here, I'm fitting VRs of different orders. So here, when I'm calling fit on VR, um, I means order. Perhaps it's better to do it like this. Or okay, so now our original model is of order 1 because today's values of y and x depend only on lag of yesterday's value, of one leg of yesterday's value. But here I'm trying legs up to 12. And then I can look at the information criteria to see which leg would be which leg the information would be selected by the information criterion. The best is the information. The leg that we need to select is the one that is maximized by the information criterion. And so here we see that, say, both Akaike and Bayesian, they somehow select, so let's say, sorry. Is it what? No. Order. By. No. So please.
I think it's by. Not just by.
Oh, okay, perfect. Thank you. So we see that Akaike gives us ascending. The biggest Akaike criterion is 12. Is it correct? I'm always
Shouldn't it be the smallest one?
the smallest one, yeah. I'm always confused.
And in our case, it's like the smallest, so like the biggest by ABC with a minus.
Okay, with the minimum. Okay, thank you. Terrible. Yeah, I'm a mess today. Okay. Okay, so it gives order one, perfect. What about Bayesian? I guess also order one, yes. It's fine for us. So then one way of checking if this process is invertible or not invertible is to check the roots of VR. And if all roots are more than one, then we are fine. So it's a stable process. If some roots are less than one, then we need to do something with it, like perhaps difference. But there are like it's whole own issue once you have having non-stability in VRs. You start running all kinds of issues. So we don't look at it because we don't have the time. Now, let's see what it gives us when we estimate as a result of estimate. So the original coefficient, this was 1. So this is a regression, the coefficients for y and x. This is for x and y and x. So this is 0.78. And if you multiply standard error by 2, then this value plus minus 0.4, standard error multiplied by 2, covers 1. So this is how we check that. Usually, just, I don't know, to give you an idea that we don't get the exact one, but with 95% probability, we cover the true coefficient. Then for x, it's not significant, perfect, and for y, it's 0.8, so we get the one that we specified here, and similarly for the x. So that's so 0.5, 0.6, and 1. Perhaps this is not so interesting. Let's see what we get for 0.4. So when we get the consider VR with log 4, we get all the logs beyond the log 1 are insignificant, which is great. But in reality, if we have a shorter time series, we might not be able to distinguish between different logs. And then usually we take the smallest log. Similarly here, all logs are insignificant beyond log 1. And yeah, matrix of residuals is what we specified before. Perfect. Now, yeah, it's good. You can test normality. As usual, we the same as what we did with ordinary least squares. We should check normality of the residuals, and if residuals are normal, then our model perhaps like VR are well suited for testing or for as a model of the data. Even I should say that then we can rely on many standard statistical tests. If the residuals are not normal, then it's not a huge issue because many statistical tests would still work in asymptotically. But then we have to be careful when interpreting their results, in the sense that we shouldn't be perhaps relying on these tests 100%. We should be relying more on our economic intuition when selecting the model. So here we test normality of the residuals, a joint normality of the residuals. And p-value is quite high. H0 is that data is generated by normally distributed process. P-value is quite high, so we don't reject H0. And the same for when we're dealing with residuals of with VR4 model. Now, this is perhaps the more important test that residuals are not autocorrelated. So let me go back here. It's fine if the residuals are like for y and x are correlated between each other. Our theory would work. What is not fine if this vector of two-dimensional vector of epsilon y, epsilon x is correlated across time as a vector. So this is not fine. Then our estimates of the coefficients will be biased and our statistical tests do not apply. So this fact that this property of residuals being autocorrelated, correlated, and drawn from the same distribution is called whiteness. So this is a white error as a vector. And this is a more important test than the test for normality. This was true with ordinary squares. This is true with autoregressive, one-dimensional autoregressive processes. And this is also true with vector autoregressive processes. That the whiteness is the most important property. And here we are checking if they're autocorrelated up to log 12. And it says that p-value is quite high, which means that it fails to reject H0. So strange. It tells us that yeah, okay, no, correct. That autocorrelation up to log 12 is 0. So no autocorrelation, and basically we confirm the same with this. Perfect. Also, we fail to reject of no autocorrelation. Now, this is all fine. The next thing that I'm going to do is to do, I haven't done this before with the rolling forecast. Is it expanding window? Let me see. I've done it some time ago. So let's go step by step. So fine. My desktop is back to life. Give me 1 second.
While you're on it, again about the autocorrelation. So it's not critical for us if the errors in the equations are dependent, but uh, besides this, autocorrelation is still bad for us, right?
Yeah, so no, that wasn't my emphasis. Sorry. My emphasis was on the fact that it's not a problem. There are several points here. One point is that do we need to have normally distributed errors? Many results of and statistical tests, statistical inference, what kind of statistical inference I'm talking about? Say Bayesian information criterion, Akaike information criterion, significance of coefficients in front of log variables, things like that. How do we select which one, how many logs we select? We can look at the significance of the coefficients. Like here, we see that all of these are insignificant, and perhaps we can drop them, or we can look at the Akaike or Bayesian information criterion or some other information criterion. Strictly speaking, some of these criteria require normal distribution of errors. However, so with normal distribution, they are exact. The t-statistics and p-values. If the distribution of errors is not normal, then they are asymptotically correct, meaning that when the sample size is large, then these are these statistical tests have the critical values that we use to calculate the p-values. Now, if our sample size is relatively large, what it means to be relatively large, I don't know. It depends on the context. But if it's large enough, then failing to have a normality of residuals is not a big problem. But failing if we have autocorrelated errors, so if residuals are correlated within time, across time, sorry, not within time, across time. So residuals for time one are correlated with residuals to like t-1. Then we are in trouble because this is perhaps not the right model. I mean, if we find the correlation of residuals, then we cannot apply just VER.
Okay.
Yes, and then this is a nature of VERs that errors are allowed to be correlated within time. That is not a problem for VER. So this epsilon y is correlated with epsilon x, and it's okay. VR assumes this correlation. One second, I'm just. Okay, so we test white here as well. So perfect. Now, okay. 1 second. So here I will be applying VR for forecasting. So I will be running so starting from some starting sample size of white train feed forecast, and then add the next value feed forecast. So this is a rolling window forecast. And this VR function, the nice feature of it, which is different from ARIMA implementation in Python, that it has error bands. Sorry, here I'm using actually, no, everything is right. Okay, sorry, I'm jumping around. So I start with remember our sample size is 500. I start with the sample size 400 and do rolling forecast of size of ARIMA of VR size 1, and then rolling forecast of VR of size 4. And here I'm doing forecast for 100 periods ahead, while here I'm doing a rolling forecast. Of course, rolling forecast with the expanding window, what we've done many times. Forecast 1 period ahead, extend the sample, include this period from the true data, forecast again, and so on. While here, I forecast all 100 periods ahead. Just this is what I called in the past static forecast. So this is just how it's implemented with VRs. You can, of course, reuse this code, and perhaps you did it for glass or trees. You just need to substitute here the specific method. Instead of VR, you substitute glass or trees. And we can plot this, and the only reason why I'm plotting this, so this is the plot of this one upper one row is H steps ahead forecast, so 100 periods ahead, with VR1, and the lower one VR, which one? 4. Right, VR4. Now, the only reason why I'm plotting this is that it's not that I want to put lots of emphasis on it, or I want you to start using such pictures. Actually, the reason why I'm plotting this is that to say that such pictures are somehow popular in forecasting, but in some sense they're meaningless. Because by just looking at this picture, okay, we see that the static forecast doesn't perform well. Well, in the sense it doesn't predict this, but on average, it's okay. It was 95%, it covers the range of values of y. Sorry, this what I was talking about. This is y, this is x, and this is all. Sorry. Oh my gosh, I'm a mess today. This is the forecast for y, this is forecast for x, and this is one period VR1, and the next one is VR4. So okay, back to this one. So with probability, with 95% probability, we cover the whole range, which tells us that it's not surprising because the structure of the VR doesn't change with time, it's stable. That's why we can use the estimated parameters to forecast very far into the future. At the same time, with the real data, the structure of VR, so of the data generating process can be changing with time. And most likely we will not be able to forecast so well into the future. And so one lesson, or not lesson, just a long horizon forecasts, they can be good in the sense that if the data generating process doesn't change with time, we will be covering the data with a 95% probability. And that's what we see here. So observe that our forecast, which is this orange line, or this one, it almost never hits the true data. I think it never hits the true data for a particular horizon. But the 95% interval around it covers most of the data. And this is what's the best we can achieve with forecasts if the data generating process is not changing. And this is what we aspire to achieve. We never aspire to achieve the exact value, which is next to impossible. But we aspire to achieve something like this. Then if we are doing rolling forecast, we are obviously doing a better job because we are at each period of time, we use all the data up to that period and then forecast one period ahead. And so here we are doing quite well. Now, we are doing quite well in the sense that we almost always cover the blue line, which is the true data with the 95% interval, and moreover, the orange line is quite close to the blue line. And this kind of figure, they're popular in forecasting. You can see them in many applications, or not applications, many papers, so like forecasting literature. However, some people in the profession don't use these figures deliberately because by just looking at them, you don't know if you're doing a good or bad job because the fact that this tracks so well can be deceiving. Why? For example, if we use for the prediction just value of y in the previous period, then we also will be very close to the blue line. And so, like, just eyeballing it will not tell us if we're doing a good or bad job. What we really should be relying on are the the loss function value. That's the ultimate way of checking if we are doing a good job with our forecast. Does this make sense?
Yes, it does. But those graphs, well, I I could conclude, as I got it, that if we want to make a forecast, for example, for several periods, we better use a static one, and we better use a rolling forecast if we want to predict for just a few periods ahead, right or not? Because
No,
static will be good on average, and rolling forecast just by its construction is bad, like in the short term.
no. This is sorry. This is no. Uh, we like at the end of the day, this is like at the end of the day, depends on what you want to achieve. If you want to achieve, why you're even calculating this thing? You're calculating this thing either H-step or head forecast or rolling forecast. You're calculating this to calculate error, forecast error on your data. And ultimately, you would be in this like end period 100, which is our data is 500 of length 500. And so ultimately, you're in period 500 and you want to predict it for the next few periods. You can do this kind of rolling forecast for 5 period ahead forecast and rolling your data. You can do 1 period ahead forecast. What's more important is that you should calculate the error and then you should compare different methods using that error. And as it comes to this static forecast, like this one, the only reason why I plotted it here was to emphasize this point that this is what we expect in an ideal situation. We never hit we can forecast quite well very far into the future in the sense of predicting the average value and covering the data with high probability with the 95% probability. And that's the best we can achieve with our forecasts. We never forecast exact blue values. But if the data generating process is not changing, then we can do very good H steps instead, like 100 periods ahead forecasts, which is a lot, by covering the possible range of values. Observe that our forecast at the end of the horizon and at the beginning, the quality of the forecast are kind of similar. They just cover the possible range of values here and here. And this is the ideal situation. In the real world, the data generating process is changing, or we don't have enough data to estimate precisely the data generating process. And in the real world, the further we go with our horizon, the worse our forecast becomes. Does this make sense now?
Yes, it does.
Okay. Anyone else? Everyone is clear on that? Okay, I hope it's clear. Now, so I skip this. This is for the 4 periods, the similar situation. So for VR4, what's more important is this, the root mean squared error. So we see that our H steps ahead forecast, we can calculate the root mean square error for Y, for X, and for the rolling forecast. They are not comparable, this one and this one, because this one H steps ahead, 100 steps ahead. This one is rolling forecast and average error. But I want to now then compare with univariate IREMA models. So now I will take these processes one at a time and see if I can forecast them one at a time using a univariate linear model. And then I will compare the errors from the univariate linear models to these ones. So to compare with the univariate linear models, yeah, 1 second. How are we doing here? Wow, it takes forever to install. This is crazy. My Anaconda is still updating for like an hour. Terrible. I have too many computers. I have like 4 computers, and I sometimes not good at maintaining them up to date. Okay. Let's see. So here, what I will be doing, I will be running IREMA, this one from this library, stats model to say IREMA. And so for IREMA, we need autoregressive order, which I will call P, then integration order, which is the amount of difference we need to make, and then MA order, moving average order, or order of correlations in the errors. And I will be going through the autoregression order from 0 to 4, and for moving average order also from 0 to 4, and integration order just always 0. And then I will evaluate these models in the loop, like all combinations of AR and MA. And I will be recording the Akaike, Bayesian, and Hannon Pin information criteria. So it's interesting to see once we take this series for y and x one at a time, which one will be, I've written it, sort function here. Too bad. Sometimes I remember, sometimes I forget how to write it. And it's interesting to see which one will be. So in our particular case, Akaike selects the AR1. Interesting. What about Bayesian information criteria? Also autoregressive one. In general, in practice, perhaps this would be a way for you to select. This is one way to select the specification. Another way is to use rolling forecast to select the model. So you can be doing the rolling forecast with different ARIMA specifications, and then select the one that gives you the smallest forecast error. Let's see which one for X is selected. Strangely enough, but that's still okay. So also autoregressive of order 1. But it doesn't have to be the case. In other examples, when I was simulating different data, it was selecting different orders. And observe that we have correlation of errors between y and of error y and x contemporaneous, but somehow it's not making it worse. Okay, now it's interesting to see which one will be the best. So this is another way of, as I said, we can do rolling forecast and select the order. So for this, I'm doing almost the same as what I did with VRs. I think this doesn't work. Does it work? Oh, yes, it does. Okay, let's see. So this is my part. Uh-huh. Haven't done. Sorry. Haven't done. Sorry. This is static forecast. Okay, this is a static forecast. One second. No. Okay, this was correct. Ah, let me see. Oh, sorry, I confused the names. Um, oh, very strange. For the 8 steps ahead, we are not doing much more different in terms of ARIMA and VR, but yeah, with the rolling forecast, we're definitely not doing well with predicting X. We can try also different orders for the rolling forecast and repeat this procedure, and across the rolling forecast, select the one that gives the lowest error here. Okay, so that kind of finishes what we can do to select the model and do the forecast with VRs, and we will apply it to the real data. Let's see how I'm doing with the installation. It's terrible. Something is it's taking forever. I don't know what's going on. Maybe I should quit this. Now, one thing that now we can do is see if there's a so two general things that we do with VRs. We test if one set of variables is impacting another set of variables, causing, and we do impulse responses. So for the course is the usual test is the Granger causality test. And here, for example, I am testing if I'm doing a Granger causality F test and checking if Y is causing X. So if you go back here, this Y is potentially causing X, while X is not causing Y. So let's check. This is the usual check that we do with VRs. We are checking Granger causality. Here, okay, Y1 does not Granger cause Y2. We can start like this. y2 does not greater cos y1, but we used VR of size 4. Let's see if we do size 1. y2 does not greater cos y1. What about the opposite? Also, sorry, what I'm saying. So the H0 is H0 is that y1 does not greater cos 1, 2, and we reject H0, which is what we expect. Now, if we do in reverse, y2 does not cause y1. Now we fail to reject H0. P-value is quite high, so we conclude with the Granger causality that one variable is causing the other. This is usually we use this kind of tests to understand the or the impact of variables on each other. And another way in which we understand these impacts, we construct impulse responses. There is some mathematics behind it that explains how impulse responses are constructed, but it's not so important to understand this mathematics, but it's important to understand the intuition. So the intuition here is the following. Imagine we estimated some model, like model of size 1, and then we get some coefficients of this model, and then we shock provide a like one standard deviation shock to the joint model of y and x, and then we see how that impacts how the impulse responses propagate. For example, we shock here y1, and we see what happens. If we shock y1, it's exponentially starts decaying, but it's not falling immediately, which means that we see that there is persistence. So this is an autoregressive process of itself. And the 95% interval is strictly above 0, so there is an influence of y1 on itself in an autoregressive manner. Then if we look at the impulse of y1 on y2, we see that there is also an impact like this, which means that there is a impact of y1 on y2. It's significantly more than 0, and these error bands are telling us this, that they are above 0. Well, then y2 in itself starts changing and it impacts y1, and this is how it looks. However, this solid blue line, how the response of y2 in response to changes, sorry, response of y1 in response to changes in y2. But this impulse response is contained with 95% probability contains the 0, which brings us to a conclusion that with 95% probability, the y2 doesn't impact y1 because 0 is included in this confidence, 95% confidence band. Now, finally, how y2 impacts on itself, it's the same as here. So this is, and this kind of figure is doing This is just repeats, but yeah, we can do this thing. Okay, yeah. So we usually with VRs, we use the impulse responses to visualize this is a usual tool used in when understanding the model when we're analyzing VRs to understand how variables impact each other. Okay. That, yes. No, impact. So we see that it's also AR process in Y2 and Y2, but it's less persistent, meaning that the AR coefficient is smaller than this one because it decays faster.
Okay.
And this is not surprising because the original model has a smaller coefficient. Here 0.8 and here 0.5. So in essence, I should say that there is way more to VRs than what I talked about today. You can spend like whole semester talking about VRs, and there are all kinds of issues, but and then all kinds of topics there. Like you need to talk about co-integration, the same as we talked about unit roots and AR processes. Um, However, like to the first order approximation, if you will, uh, this is enough to start working with VRs and using them for prediction. Uh, this simple example shows you that um, perhaps sometimes, even though we have basically the message is the following. Remember the Wald decomposition theorem that tells us that everything, in order to predict the process, everything we need to know is just the full history of this process. And then if we know it, we don't need anything else. We should be able to predict it. And this is kind of what we are finding in this particular example. We generate y and x with some complicated interdependence, but we are doing quite a good job with forecasting them using just themselves. So this shows you the power of the Wald decomposition theorem, and it also gives you an idea why people use ARIMA processes as a benchmark. They're usually relatively simple to estimate and difficult to beat if you have enough data. And so this is one message of today's exercise. On the other hand, we never know how much data is enough. For example, if I reduce T to like say 100, then perhaps VR will be much better. So we can try checking if there's 100. Let's see what. Yeah, VR still gives us one period, in terms of VR of order one, in terms of Bayesian and archaic information criteria. Now, if I skip to the forecasts, I should say I use train size. Mm, so, like this. No. Mm, mm. Um, no. Um, mm, mm. No. What's going on? Let me see. Mm. Oh, I see. Let's see. Well, still gives quite a good performance. Let's compare it. So this is both in terms of X and Y. I don't understand what's happening. Oh. I don't understand. 1 second. Hmm. Mind blowing. What's going on? Oh.
test size is an int, right?
Yes. And I think this is how it's supposed to be. Yeah. Mind blowing. Wow.
Maybe you
That's
should
why, yeah.
restart just the whole notebook. Maybe
Yeah,
something has
good.
overwritten.
Yeah, good point. That's why I, Python is very beautiful and flexible, but I actually I really hate the weak typization. I saw like C++ with its strong typization. You never make such mistakes in C++. Um, okay, this is all doesn't matter. Hmm. Oh, this is an example where it gives us ARIMA 101 for Y. I think it's the same for X, according to Akaike's. No. Mind blowing. I don't know what's going on.
Maybe we should move to other part, like with
Okay. Yeah, I don't know
arena
what's going on.
forest and
Yeah, sorry. Bizarre. I think I need to one last try.
I think it's maybe written in the stats models documentation that there may be additional arguments required if forecasting beyond the end of the sample.
No, it shouldn't be the problem because we're definitely forecasting beyond the sample. I'm just giving it this train, and this is the sample. And now I want to use this sample to train the model and then forecast several periods ahead. So something is, yeah, let me just try this last time. Okay, it didn't work. Forget about it. I don't know. We'll figure it out. This is bizarre. Wow, I have never seen anything like this. Yeah, Python has a long way to go to being as good as C++. Okay, this is a very weird behavior. So anyway, the point was that what I was trying to make is that perhaps if you reduce the sample size, then ARIMA will not be as good as VR. Okay, let us move to perhaps let's make a like a 10-minute break and then I'll do the trees.
okay.
Trees are not so difficult and they're not they're not used so often here. Let's okay, perfect. Thank you. So it has to be int here it has to be int um mhm. There it is. Uh-huh. Now it works. Thank you very much. So it was about converting it to int. Oh, terrible. Yeah, it doesn't perform much worse relative to VR, although the for prediction for Y all the prediction for X is worse. Anyway, let's go to, so we settled this, great. Let's go to the trees. So with the trees, there is not much, I don't want to work with like random forests or begging trees, because they're usually not so good, and in practice you would, in the real world applications, you would rarely use them. But boosting trees, this is a killer thing. So most the entry point, so you don't need this. The entry point is AdaBoost regressor. That's where you should start. So let me restart the kernel. Mhm. So I'm loading the same European data that I used before, GDP, consumer confidence indicator, and so on. Now I'm going to apply an AdaBoost regressor to it. And we have two options: number estimators, which is the number of the iterations we are going to be applying the AdaBoost regressor, and the loss. The variance, the options for the loss are linear, square. We can see here what it gives us. We can do linear or square. I'm going to use square. If it's a regressor, we can also use AdaBoost for classification, but we're not going to cover it in the tutorial. We'll be using only regressors. Then once we specify this AdaBoost regressor, everything else goes as usual. We feed the data, then we predict, and we can calculate the regressors, I mean the predictions. AdaBoost regressor is a nonlinear method, and in that sense, it might be a bit black boxy. We don't know which are the variables that impact its performance, or why it's making certain predictions. But because AdaBoost is based on trees, we can use the so-called feature importance. So here I am wrote a little piece of code to check feature importance. I'm using this feature importances field or attribute of the result of AdaBoost regression. I normalize it to the most important feature. I normalize to 100%, and the other ones scale relative to it. So, and then I make a graph, a bar chart. So what comes out of this is that the most important feature from the perspective of the trees consumer confidence indicator and industrial production index. And if you remember, these variables were actually insignificant in the regressions. So it's interesting that in the linear regressions, when we're using linear regression of GDP on all these variables, consumer confidence indicator was insignificant, but it was industrial production index that was important, and its lag. Now its lag has less importance, and industrial production indicator is almost 1/3 less important as consumer confidence indicator. Industrial production index is 1/3 less important than consumer confidence indicator. Now, what is the importance? Importance is some average value on how often this variable, how much this variable reduces the error on the train data set. Now, we can do, once we train the model, once we train the tree, we can do all the same stuff to select each hyperparameter. Yes?
So again, importance, it's like how many times it was used to build a particular leaf of the tree, or not?
No, not a particular leaf of a tree. How much it resulted in the reduction of the error.
Okay.
So when we're using this variable in any branches of the tree, to then like go left or right, depending on the threshold of this variable, we reducing an error to some extent, and then there is a way to calculate how much we use this variable to reduce the overall error on the trained data set.
Okay.
Now, I didn't install XGBoost on this laptop. It was installed on my desktop, and also Google has it. I mean, Google Colab has it. So, but you can use XGBoost regressor. XGBoost is an alternative library to AdaBoost. AdaBoost comes with a standard Python distribution, and you just use it like this. So very easy, nothing different in terms of using it. It's not different from using, say, Lasso or Arima. It's all the same stuff. Model, fit, predict, or forecast. All three commons. It's usual stuff. And this is what is nice about this whole set of functions in in Python. All functions are obeying the same standard. Model, fit, predict. XGBoost is the same, but I didn't install it here. And now it's like my Jupyter notebook environment has been installing for 2 hours. I don't know what's taking it too long. And I don't see any end in sight. Seems like to be stuck. I vaguely remember that a few years ago, my Jupyter notebook environment was reinstalling for like a day, which is not unheard of, because whatever they're making, I don't know how they implement the update, but update of Jupyter notebooks locally is always a pain. So I'm not going to demonstrate it, but I want to say that XGBoost is the most advanced library in Python for using boosting trees. And in real world applications with lots of data, you should be using XGBoost. It has the same idea as AdaBoost, but it's as general as gradient boosting trees, and it has lots of improvements and a bunch of hyperparameters that you can choose. And so in practice, people who achieve amazing results with forecasting or prediction, they're using XGBoost usually. But for our simple example, AdaBoost is as good. So once we have this general structure, we can apply AdaBoost to rolling forecast or static forecast, whatever. So let me remove all this stuff. Okay. And let me remove XGBoost. Now,
Maybe
there is
you
one. Yeah.
maybe you shouldn't have removed XGBoost just for us to have the code.
Okay. But it's the same logic. Yeah. Let me. Oops.
Thanks.
You're welcome. Okay. Now there is one hyperparameter that you should choose. Is this m? Is the number of estimators, so the number of iterations you apply regressor to improve errors. So we did this with Lasso. Let us do this. Say, hmm. doesn't look like, yeah. So when we train trees of different sizes, it seems to be, so this is mean squared error, right, on the test. And it's jumping around. And one reason for this is that I think AdaBoost regressor is using, let me see, is it using random forest inside? Random square random. Okay, so it's using random forest. Let's see the random scene. Let's reduce the learning rate actually. It's a good idea to put a low learning rate. Usually we want lots of weak estimators with a slow learning rate. Then how do we turn off the decision tree regressor so we can, let's see. Um, let me sample screen. We can also adjust the, so let's decision tree regressor. We can adjust the parameters of the decision tree. Let's come back here. No? I have an old version. Okay. So let's see. Let's do max depth 1. And let's do this here as well. The tree of size 1 is called a stump, and usually, I think in my practice, for the boosting trees, gradient boosting trees, I guess, yeah, using the tree depths has a tremendous impact on the performance. So we have several hyperparameters. This number of times we do it, the learning rate, the depth of the tree. Let's see how it behaves now. Aha. Now we're talking business. So now we keep reducing the error, but still there is randomness. How do I remove this randomness? Last random state. This is meter. Splitter. Best. Let's make more steps. Doesn't look like we're gaining anything after m equal to 50, so we might as well just stop at 50. Um, let us see how it performs. So that would be at 50, we would get something like 0.835. Let's see if we allow tree depths of 2. It's not good. Yeah, you see, we are not getting much improvement when we allow the depths of trees to be higher than 1. Yeah, we get improvement somewhere at the beginning, but that seems to be...
Maybe we are just overfitting them.
Yeah, we are overfitting. So obviously we are overfitting the data with depth equal to 2. That means that there is not... So what it means when we increase the depths of the trees, it means that we are allowing interactions between variables. When the tree size is just 1, then each time we are doing a split on just one variable. If we allow depths of equal to 2, for example, then our split will be on one variable and then potentially on another variable. that allows for non-trivial interactions with variables of like order of 2. If we allow depth 3, then it would be order of 3, and so on. And so allowing these interactions potentially overfits the data. And so we see that perhaps having depth equal to 1 is the best. Yeah, so we get a nice result, and it's not clear where we should stop. But perhaps, as I said, somewhere like at 50 is good enough, because after 50 we don't have much improvement. We can also see if changing the learning rate would be of any help. So we achieve.
In practice, could we just check different specifications and choose like the best one? So learning rate and max depth and their criterion, so the error, well, squared error, they are just the parameters. So we could just like to iterate through them, like check the combinations and choose like the best one.
Yeah, so in practice, perhaps this is what you do, although and on top of that, I'm doing here a static forecast. So I'm using one tree to forecast all the data. So I split the sample into train and test. How much did I devote to train? Everything but the 8 last observations. But in practice, you would do like expanding window forecast, one horizon ahead maybe. So that would be one loop, and then plus loops on hyperparameters. But the problem with this is that it can take a long time to choose the best model. But on the other hand, ideally, this is what you should do. But if it's costly to estimate each model, then you should come up with some kind of heuristics, which model you think would be the best. Or like, sorry, which not model, which hyperparameters can be the best.
I know that combining some economic judgment about the parameters, like that a learning rate higher than 1 is it could be strange, and so on. And some how to say, some packages which help us to do these iterations, like not all of them, but only part of them, like UpTuner. It could really fasten this process of choosing like the best ADA boost model or any kind of boosting model.
Sorry, could you say it again?
Yeah. So the problem with the approach of iterations, it's like if we have 3 parameters, we'll do like 3 cycles. It's like n in the 3rd degree, and it's a lot. And if we have like parameters, I don't know, k, it will be k in the power of n, and it's like really a lot. But we could like do several things. For example, we could restrict the space of our parameters by our understanding, like that learning rate in this particular problem shouldn't be like too high or too low. And also,
Right.
we could use something like uptuner in Python to like not do all the iterations, but some part of them.
Yes, yes. And yes, this is correct. One thing that you've said that we can be choosing the criterion. Criterion is the squared error. We should choose like it everywhere, like here, here, uh, and then when we are evaluating, I'm using the same. We should be consistent. Although we can be choosing this loss and this to be different. So when we are building a tree, we can be using a different criterion from the other boost regression. This criterion would construct a tree, and this would choose a prediction on at the leaf of which at each leaf of the tree. So this can be different, but it depends on what you want to do. Usually we settle on one loss criterion, and then we use the same loss criterion everywhere consistently. So this part we don't change much. Everything else we do it in a loop, and as you said, like for example, learning rate, perhaps we don't need to optimize on this. Then M, we could potentially, instead of doing it like this, we could potentially do something like um, this. If I am correct. Yeah, although perhaps one like this. Um, we don't need to go through all M sizes. We can be increasing them by 10, and it's good enough. Maybe by 5. Maybe, let me see. Like this.
The third value is the step.
Yes. Is this correct? No, I guess it's not correct. This is correct. This. Um, So this is one improvement that we can make. To make it faster, and we see that as we go along, like increase this number of steps by 5, we pretty much still like stop at 50. So we can stop. There is some improvement here, but it can be just because of whatever. Perhaps it doesn't, because all the number of steps around it doesn't lead, the values of m around it don't lead to a better improvement, then we don't trust this particular value. Rather, we trust like on average. And so we see that perhaps with the 50, size 50 is a good number. Okay, I guess we stop here. Not much. Sorry for lots of technical issues today. It was it was a very hard week for me. Uh, so I will give you an assignment today, and then I will see you all next Tuesday.
Okay, thank you. Goodbye.
Bye.